Okay, now let's look at the quiz. And it says, suppose you want to find an 86% confidence interval for the proportion of all Americans who are truly practicing safe social distancing. If you want a margin of error of no more than plus or minus 3%, how many Americans must you survey? Be sure to show your work similar to what was done in the webinar and not just give the final answer. Okay, so the first thing you should do is decide what kind of question is this. First, what are we looking for? What are your thoughts? What is the question asking for? Maybe in one letter. Yeah, this is an N. This is a find the sample size question. Okay, so this is a find the sample size. And the next thing, so let me just write that down. We want to find N. So next, let's see what kind of find N is it? So the first, is this a quantitative survey question or is this a qualitative yes/no survey question? What do you think? Yeah, this is the qualitative yes/no because the survey question is, are you truly practicing social distancing? Okay, or maybe you're going to watch somebody and see if they're practicing or not. Okay, so note this is a yes/no question. Let me write survey question. So I always like to go through the thought process so that you can get this stuff, especially for exam, because that's what matters the most. So next, there's two kinds of yes/no questions. Do we have an idea or a preliminary estimate for the population proportion? Or do we have no estimate at all? Yeah, there's no estimate here, so no estimate. For P. So in that case, we have a formula for the yes/no, and that was N was equal to 0.25 times Z over E squared. Any questions on coming up with, that's our strategy. We need to find that formula. Any questions? All right, so we need to figure out what is E, because that's E for easy, let's call it that, but it's actually E for error. So what is E in this case? Yeah, 0.03. You don't need the minus, the plus or minus, because you're squaring anyway. So E is 0.03. Now what we need to do is we need to find Z, and that's usually the harder part. And we have an 86% confidence interval. Okay, so we need to use that. So is 86 what I'm going to put in the calculator, or 0.86? What do you think? Yeah, definitely not. Because remember, there's 86% inside in the confidence interval. That means there's 14% outside the confidence interval. Half of that is 7%. Any questions on that so far? Okay, I decided, and I wasn't sure, I never know what's going to work and what's not going to work. You can tell me. I decided not to link you guys to the calculator in this one because I thought, since this is a quiz, which means there's no Proctorio, you can actually go out and use and find an outside resource. I was hoping you would be able to find it because I want to encourage you to know how to find it. On an exam, it would be definitely embedded in. But I decided for this one, let's try not embedding and see if you know how to find it. Were you able to find the calculator? Good, good. And if you found my calculator, then you went to the normal probability calculator. There's a lot of others out there too. I don't want to say I'm the only person that's ever done a calculator, but I wrote this one. And again, we wanted, let's look at this again, 86% confidence interval, so 7% to the left. So that means P is 0.07. Any questions on that? Okay, yeah, no calculators is usually a hint, but again, quizzes are low stakes, so you're not supposed to be stressed about quizzes. So because this particular quiz didn't have a lot going on, so we did the kind of longer stuff last week on Thursday, I decided to, let you go look for that calculator. That was the reason. Okay. So we know that. What's the mean? Whenever you're doing this kind of problem, what's the mean? Yeah, the mean is 0. And what's the standard deviation? 1. Okay. What's the low? Yeah, a bunch of 9s with a negative 9, however many you want. And then I hit calculate. I'll just copy that guy in. And let's write z is equal to. Now I can paste it. Any questions on that? Okay, so now again, you can go to a kind of a standard calculator and we can just plug in. So let's do that. I'll just use the Google toolbar. So remember, n was equal to 0.25 times parentheses, and then that messy z divided by 0.03 squared. And you get 604.988655. How many people should we ask? 605. So survey. 605. And these are Americans. Any questions at all on question 1? Any questions? Okay, let's look at the next one. Okay, suppose you want a 90% confidence interval for the population mean time it takes people to shop for groceries. If you want a margin of error of no more than plus or minus 0.5 minutes, and a preliminary study gave you an estimate of 7 minutes for the standard deviation of the time it takes to shop for groceries, how many people must you observe shopping at grocery stores? Be sure to show your work similar to what was done in the webinar and not just give a final answer. Okay. So similar to the last one, what kind of problem is this? What are we looking for in one letter? Why do you want us to work these out with equations if we can just plug into the calcs? If you go to the real calculator, then the equations happen. Okay. There is one particular calculator, but I don't think I embedded it in that list. So you need to be able to plug in the equations because that's what you're going to be given the, you'll be given the ability to find the inverse norm. In other words, find your Z if you know your probability. And that's about it. Yeah, so that it's a tough question. I understand what you're asking. The funny thing is, I actually got criticized for publicizing that particular app. Some of my colleagues from different colleges weren't very happy about it because then they said then students don't have to do any thinking. And the idea is this way it forces you to be thinking about the normal distribution. Now talk about the app. So the embedded you're talking about I'm not talking about the app, talking about the embedded calculators. Right, there is an embedded calculator that does it, but not the one on the list. $10 and $12, let's take a look. Yeah, it is there, but I do want you to do it the other way. It's better to do it the other way because one of my colleagues told me that I wasn't, yeah, it had to do, I was okay with this and then I got slammed for it. Like I said, it's one of the things you learn your lesson. I wrote something and then some people at, believe it or not, in Oxnard and in the Bay Area, some faculty weren't very happy about it. So it's a hard one for me. So sorry about that. So I probably shouldn't have even made that calculator because people didn't like it because it was too easy in a way. Yeah, it's a little frustrating. Sorry. That's why I didn't show that to you. Notice I never showed that to you in lecture. You found it though. Okay. All right. Suppose you want to be 95%, 90% confident for the population mean time. Okay, so in this case, what do we want? In one letter, what are we looking for? Yeah, N. So I'll just write N equals question mark. And is the survey question quantitative or is it qualitative? Yeah, this one's quantitative because what you're going to ask or what you're going to watch is how many minutes did you spend in the grocery store? And someone might say, I spent 32 minutes. And that's a number. It's not yes or no. Is that clear? Very, very important in this class. That's literally the first point of entry in just about every problem that we do from chapter 8 on, is to understand whether it's a yes/no question or whether it's a quantitative question. So this is a quantitative. Okay, so since it's a quantitative survey question, then that means that we're going to use the formula. N is equal to, and now we have a parenthesis, we have a fraction, we have a z. So we have z sigma, get that sigma in there, over E, and then squared. Any questions on that? Because that's the quantitative. Okay, so now we gotta get what we know, and I like to just go through and read the numbers that are given. We want a margin of error plus or minus 0.5 minutes. So what letter is that? What letter is that 0.5? Yeah, that's E, equals 0.5. And preliminary study gave you an estimate of 7 minutes for the standard deviation. That is, I'm just going to write sigma, which is Greek letter sigma, is equal to 7. We want a 90% confidence. So in particular, for the 90% confidence, what's going to be our P that we're going to plug in? I'll start with 0 point. What's the P that we plug in? Yeah, 0.05 because 90% inside, 10% outside. Half of that is 5% or 0.05. Any questions on that? Okay, so now let's go, and I'm not gonna use the really easy one because I was, like I said, I was scolded for it. I'm sorry about that. That happened very recently, by the way. So, I don't know what I'm not supposed to tell you. I'm not supposed to give you that information, I guess. You like that one? Yeah, I liked it too, but my colleagues didn't. So now I'm feeling like maybe I shouldn't have done it. Okay, so very similar. We're going to have our low is -9999. We have our mean. Again, let's go back. Wait, did I get the right one? Yeah, the mean was 0. the standard deviation was 1, and our P was 0.05. And we hit calculate. Okay, this one's pretty easy to use too if you know how to do it. And this forces you to understand the relationship between the normal distribution and these confidence intervals. Okay, and you get 1.6 4, 4, 8, 5, 3, etc. I'm just going to copy and paste it. Okay, most people call this 1.645. This one's a kind of a famous one. So I figured I'd give it to you since I hadn't used this one yet. So 90% is kind of common. So now what we're going to do is we can just say n is equal to z. Well, let me just write z and then we'll stick in a calculator. Z equals this big fat number. And again, we have a sigma 7 is 0.5. So now I can go in. And let's redo it. So we have that messy thing times 7 divided by 0.5 squared. Okay, and lost it. There we go. Okay, so do you remember how rounding rules work? In this case, this is like the weird case. Yeah, you always round up when it comes to finding a sample size, because that way you're asking one extra person is no big deal, and then you're guaranteed. That's the whole point, is you want to be guaranteed. So 531. So where are we? There we are. Survey 531, 531 people. Okay, who are we surveying? People in this case. Any questions at all on the finding the sample size quiz questions? Any questions on that? Okay, again, I want to mention a main thing, and that re-mention, and that is the number one mistake people have on this problem when it's an exam problem and you've had a lot of different stuff going on, is actually being able to decide whether it's quantitative, whether it's a yes/no question, or whether it's a qualitative, and whether it's a quantitative question. So that one we want to practice. So these are a couple good practice questions, but there's a lot of others too on the homework, for example. So make sure you practice examples, not just for finding sample size, but just general examples where you have to decide whether it is a quantitative or is a yes/no question. If you get that wrong, it's over for you. Okay, so that's like the number one most important thing for this problem, and not just this problem, but pretty much everything we're going to be doing for the rest of the class. So you got to get that one straight. Any questions at all about the quiz? Any questions? Okay. So if there's no questions, I want to talk about, I'm going to give you a current event so that we can use it as a reference. And let's do that. And I'm going to pop this one in. Yeah. It's a little frustrating this quarter, actually, because of the coronavirus, there actually aren't that many polls being taken right now, because nobody's working. And it takes people to work and make polls happen. So it's taking a little longer for me to find surveys than it used to. It's a little strange. Life is different. I think you're all used to that. Let me make this look bigger. Actually, it's too big. There we go. Okay. So this is a Quinnipiac poll. This is actually kind of cool. I'd never heard of this university. I don't know if you've heard of it. Quinnipiac University. But they do really good job on doing surveys and publishing them. So I want to look at the kind of title, and that is the majority say months, not weeks to reopen. Okay, Quinnipiac University poll finds. Okay, so I have a question for you. It's not that hard a question, but a lot of people stumble on it. What's the definition of the majority? Yeah, so more than 50%. Okay, so I want to mention that because some people make this error. It's not at least 51%, it's more than 50%. Okay, so here, what we're saying is do more than 50%, take months, not weeks to reopen, or think that it'll take months, not weeks to reopen. Okay, does that make sense to everyone? Okay, so that's the first thing, is that when you are conducting what we're going to call a hypothesis, the very first thing you're going to do is decide on what you're hypothesizing. Okay, so in our example, the question was, do the majority of Americans think that we'll reopen in months, not weeks? Any questions on that? Okay, so this is going to be the structure of hypothesis testing. And that's the very first thing you do, is you come up with your hypothesis in words. Think about what is it you think is right. Okay, then the next thing you do is you turn it into symbols. And I'm going to write it a little more formally. Write out the null and alternative hypotheses. Okay, so this is some new language. There's a lot of language in this class. I don't know if you've noticed that, but we're going to continue having a lot of language. Today's a big language day, so just to note, get these words down because you need to know them. The null hypothesis is kind of the status quo. What you're trying to show isn't correct. The alternative hypothesis is what you're trying to show is correct. So in this case, if you want to show the majority will open in months, not weeks, then the alternative hypothesis will be the following. Make it possible. So first thing is we always write that down. Any guess on what H stands for? H sub 0 colon. What's the H stand for? Yeah, H stands for hypothesis. So that's why we use the H. The 0 is just, that's what everyone uses. Okay. But I will tell you, that's not what people call it. They don't call it 0. They call it H naught. Okay. Any guess on why you call it naught instead of 0? Not a math question, really. Kind of mouthy, but not that mouthy. Any guess on why you might call it naught instead of 0? It's a good try, except actually it's not spelled N-O-T. It's N-A-U-G-H-T. So it's a different knot. Okay, and I'll tell you, because the British got to it before the Americans. Anyone ever been to England or British territory? And you hear them speak? They don't say zero, they say not. Okay, so that's just something to note, is that we're always going to use the word N-A-U-G-H-T, and it just means zero. Okay, so again, a lot of vocabulary today, and that's what everyone calls it. So the Brits got to it, and we're stuck with their weird way of talking. So H naught. And then the next thing we need to do is we need to think, and it's very similar to what I asked you on the quiz that was really important, and that is, what kind of variable is this? Is this a quantitative variable, or is this a qualitative yes/no variable? What do you think? Yeah, you got, so it says yes/no, you got to imagine with the survey question. The survey question is, do you think we'll reopen in months, not weeks? And the person's going to say yes, okay, or maybe no. Okay, they're not going to say 47.3. Is that clear to everyone? Okay, so that's really important, is to be able to take the survey question, or take the situation, think about the survey question, and decide if it's going to be a yes/no answer or a number answer. Okay, throughout this whole course, actually, it's a big part, and it's also something people stumble over. So that's why I keep saying it, and I will keep saying it. So when you have a yes/no question, P is the letter we use. We've seen that before. Now, with hypothesis tests, we're always going to use equal. Okay, there are some statisticians out there that don't, but I found that most use equal, and I try and do what most people do. Okay, so we have P equals. Now, what number should that be? So if we were wrong when we thought the majority of Americans think that we will reopen in months, not weeks, then what should P be equal for us to be wrong? Let's just put, what's the biggest P that it could be? Yeah, the biggest P it could be is 0.5, 50%. Any questions at all on H naught? Any questions? Okay, so now what we're going to do is we're going to write down what's called the alternative hypothesis. There's actually two ways of writing that, and I'm going to use what I think a little more people use nowadays. I think go back and forth, and I use what the majority tend to use. And that is H1. You will sometimes see this as H sub A instead of H sub 1. Sometimes you'll see it as H sub A because called alternative hypothesis, but I think I've seen it more as H1. I've seen it both though. So you should know how to recognize both. All right, so the first thing, or the next thing actually, is now we need the alternative hypothesis. That is what we're trying to show is true. So that's what we're trying to show is true. The majority of Americans think that we will reopen in months, not weeks. So how in symbols, how do we write this alternative hypothesis? How do you take that sentence right there without the word do and make it in symbols? And it's not like real technical, that's a hint. Yeah, exactly. So we're still going to have P for proportion, population proportion. And now it's going to be a greater than 0.5. We often call this a right-tailed test. And I'll show you why. So we call it a right-tailed test. I'm going to draw a picture. So we want to show that P is greater than 0.5. So let me show you the kind of the whole purpose of what we're doing here. Oh, shoot, I want an equation. I know why I can't see it. One more time. Okay, so the first thing is one of the things you always want to do is a big sample size. If you have a big sample size, then you know you have a normal distribution. Okay, or at least approximately normal, good enough. So that means I can draw that. Or at least I can do my best at it. That was a pretty good one. Okay. Yeah, I got lucky on that. You've seen me do some really bad ones. This one wasn't too bad. Okay. All right, so what we do is we're going to say, what if the null hypothesis is correct? Well, if the null hypothesis is correct in this case, then what does it mean? Looking for a number. Yeah, 0.5. So if the null hypothesis is correct, the mean will be 0.5. Okay? What's going to happen is there's going to be a survey taken. That's how everything works in statistics. And then what we're going to say is that if we're close to 0.5 or to the left of 0.5, then we don't have much evidence. We're not going to be surprised at all. We're not going to say it can't be true. On the other hand, if let's say 90% of the people that you asked, and you asked thousands of people, and 90% of them said it's going to take months, not weeks, then at that point, you're going to say, you know, those people are saying that's only going to be 50%. They're just not right, because that shouldn't happen. You shouldn't get 90% of your survey, if you have a large sample, saying yes when 50% of the population would say yes. So the way we draw that is the following. That's the first thing. We put this right here. And then what we're going to do is we're going to shade in, and I'm going to scribble in because that's all I can do on this. We're going to scribble in that area. And we're going to say that if it would be really rare to have like 90% of the people say, yes, it's going to be, you know, months, when 50% of the whole population say that it's going to be months, then we're going to say, you know what, the 50% just can't be right. Does that make sense? Kind of like if I flip a coin 100 times and I get 95, let's say I get 92 heads, what are you going to say about me? What do you think you'd say? If I flipped a coin 100 times, what do you say? Why wouldn't the shaded region be everything to the right of 0.5? That's a really good question. Okay, let me do the coin toss one because it's a little easier. Okay, if I flipped a coin 11 times and got 6 heads, do you think I'm cheating? No, but you know, I'm supposed to get 50% heads, right? And I got more than 50%. So why do you think I'm cheating? Okay. All right, what if I flipped a coin 6 times? Let's say I picked a coin 10 times and got 6 heads. Do you think I'm cheating? How come? That's even now. Why? It's different every time. Okay, what if I flipped a coin 500 times and got 499 heads? Do you think I'm cheating? Yeah, how is that different? How's that different from 6 times out of 10? Okay, sample size, but what if I flipped a coin 1,000 times and get 501 heads? Do you think I'm cheating? Yeah, still got a big sample size. It's not just a sample size. Do you see? It's something else. And what it is is this very far? Is it a very low probability of getting that event? And if it's a really low probability, then you're going to say, yes, I think the person's cheating. You see that? If it's not that low a probability, if it's, let's say it's 40% chance, the person might not be cheating because 40% doesn't raise your eyebrows at all. Does that make sense? So I really like that you asked that question. Why am I not shading it? Everything is right at 0.5 because it's kind of the whole crux of what we're doing. And that is, it's not that the sample has to be greater than 50%. It's that the sample has to be so much greater than 50% that you're going to say something fishy is going on. Does that make sense? So that's why I'm shading far right and not only right of 0.5, because I'm only going to shade in where it looks fishy. That's a good point. What is the definition of fishy? Very important. Okay, so the standard definition, and we've seen this before, is 5%, right? And we've seen the reverse of that. If there's 5% chance of being fishy, right? If there's 5% chance of it happening, then there's 95% of it not happening. Is that clear? And we've seen the 95% confidence interval, similar to that. So let me write down, and again, it doesn't always have to be 5%, but 5% is kind of the standard, and we're going to talk about that a lot today. So this, I'm going to say 5% or 0.05 standard, and we call it the level of significance. Any questions on that? Gonna write lines. Any questions on that idea? Okay, so that's what decides it, is that the standard is 5%, and then we'll talk about whether you want to go above or below the standard in your particular study. We're not quite ready for that, but we will be soon, in not too many minutes. Okay, then what's going to happen is you're going to do the study. Okay, you're going to do the study and you're going to get a sample proportion. Okay, you're going to get a sample proportion. So if you get a sample proportion that's way out far to the right over here, then you're going to say it's too fishy. And we're going to say this 0.5 is just a lie. On the other hand, if you get a sample proportion that is not far to the right, then you're going to say, well, maybe the 5% is right. I don't know, but I'm not ready to make an accusation. So we have some names for all this stuff. This is called the fail to reject region. And this guy is called the rejection region. Okay, and that's because if our sample proportion lies in this area over here, then we're going to say, I'm going to reject this 0.05 fact. No, it's not 50%. It's more than 50%. It really is a majority. On the other hand, if it lies outside of that rejection region, if it's over here, then I'm going to fail to reject, and I'm not going to be able to say the majority thinks that it's going to be a month. Any questions on that so far? Okay, let me ask you something. Not a trick question, that's a hint. Why do you think I called this a right-tailed test? Yeah, the rejection region is to the right. Could you have a left-tailed test? Yeah. Okay. So if your alternative hypothesis has a less than instead of a greater than, then it's a left-tailed test, because then everything's gonna be on the left instead of the right. Okay, and that would be, you might say, well, you know, I'm gonna hypothesize that that let's say fewer than 50% of Americans are making the same amount of money that they used to make before. Okay, since this virus issue. Well, that's a fewer than is going to be on the left. Do you see that? Okay. Are there any possibilities besides the left and the right? Any thoughts? Any guess? Yeah, but we don't call it both, we call it two-tailed. So you could have a two-tailed test. Any thoughts on what an example of a two-tailed test? Majority is always a greater than. The word majority means greater than. Does that make sense? You could say different from 0.5. That could happen. But how about a real world example where that's what you care about? All right, let me give you one if you're not coming up with one. Okay, let's suppose that you are a healthcare professional and you want to decide whether somebody's sick or not. Okay, you got a group of people and you want to find out, is this like a sick group or not a sick group? Okay, you take their temperature. Okay, if you're healthy, what should your temperature be? Yeah, 98.6 if we do Fahrenheit. Okay, so 98.6. What if you have a 91? What do you think? Do you think the doctor, the medical professional is going to have to do anything? You have a 91? Yeah, you might be dead. Okay, then it may not be the medical professional, then it's the coroner. But let's say you're alive, you have 91, it might be dying, right? Okay. Similarly, if you have 105, Also, you might be dying. So either way, either side of it is bad if you're far from the mean. Do you see that? So that would be an example where two-tailed might be the right way to go, because you want to find out healthy or not healthy. And healthy means you're at 98.6 or pretty close. And unhealthy means you're far in either direction. Okay, and there's a lot of examples like that. Blood pressure is another one of those. Okay, ultra low is bad, ultra high is bad. Okay, so anytime where you want to look to see is someone far off from the mean or the expected proportion, then you're going to use two-tailed. And that can happen. Any questions at all? And with two-tailed, by the way, instead of with a right-tailed, it's greater than. With a left-tailed, it's less than. What do you think the symbol is for two-tailed? Yeah, the not equal to sign. Okay, so I want to kind of go through all the different things that could happen while we're looking at this picture. Okay, any questions so far? Okay, so once you've written out your null and alternative hypotheses, and it can't hurt to draw a picture, okay? Then, actually, our number 3, the next step is decide, actually, I think understand might be the idea, the ramifications of a type 1 and a type 2 error. Okay, first thing, I just want to see how you guys are with English. Do you know what the word ramifications mean? Anyone know what ramification means? It's an English word, it's not a math word. Sometimes that's harder. Branching out, not quite. Good try though. All right, if you don't all jump in, I'll tell you. Okay, the word ramification means the consequences, the bad stuff that happens because of it. Okay, that's what ramification means. So first thing, these are errors. Errors are bad, right? Otherwise, it wouldn't be called an error. And we want to find out what bad stuff happens if you have a type 1 or type 2 error. Okay, so let me define what type 1 and type 2 errors are. Otherwise, you have no idea what I'm talking about. So let's write down definition. A type 1 error occurs when the null hypothesis is true, but we end up rejecting the null hypothesis. And deciding that the alternative hypothesis is true. Okay, so that's the definition of a type 1 error. Let me highlight some stuff. Okay, so there's a type 1 error. Okay, so in this case, what does that mean? What would happen in a type 1 error for this example that we're looking at? And this particular example is not that exciting, sorry. But I'll give you some examples of some exciting type 1 and type 2 errors. thoughts? Yeah, so it is 50%, and we rejected it, and we decided that, so we decided that the majority of people think that it's going to be longer, or maybe even want it to be longer than a couple weeks, when actually it's not, okay? Actually, most people, okay, or at least don't think it's going to be so long. Does that make sense? So that's a type 1 error. Okay. In medicine, do you know what you call a type 1 error? I've asked you, are any of you in medicine? Any of you going into some kind of medical career? Okay, maybe. So what do you call it? What do you call a type 1 error in medicine? This is very important, by the way. You never heard of it? Okay, if you don't tell me, it's a false positive. Okay, so that means a great example that everyone knows now is LTCC. There is one reason why you are allowed to go to LTCC and go inside. Okay, what is the only reason that you're allowed to go inside? And me too, by the way. Anyone you know? There's only one reason why you're allowed to go to the Lake Tahoe Community College, to go inside. Turns out inside the gym. And there's only one reason why you're allowed to, and anybody can. You don't have to be a student. None of you watched the news? Yeah, yep, yeah. LTCC is now the Corona Test Center, okay, for Tahoe. So a type 1 error means that we think that the person tests positive. So we say, hey, the person has it. But in reality, what's true? Because that's what a false positive means. So it means we think they have it, right? They test positive, and then they don't have it. What are the ramifications? What are the ramifications of a false positive in that case? Any thoughts? So that'd be like a type 1 error. What are the ramifications of a type 1 error? Any ideas? I don't see y'all jumping in, but please. So what would the ramifications of a type 1 error be when it comes to the coronavirus testing? You know, all jumping in. Remember the word ramification? Bad stuff that happens. Okay, if you don't jump in, maybe I'll mention it. Okay, so what that means is that you had that we're giving people false positives. Okay, so we're telling people they have it and they don't. And what the ramifications are is, yeah, longer quarantine. Okay, coronatine. I like that word. I haven't seen that one before, but that's pretty good. So that means we're going to send people in their houses or their apartments for weeks by themselves, lonely, and not allowing them to leave, basically. And it turns out they don't even have it. and they shouldn't have to be fully quarantined. Okay, that's a pretty bad ramification. Okay, now let me move on to a type 2 error, which you might be able to guess because it's the opposite, kind of like an opposite of a type 1 error. A type 2 error occurs when the null hypothesis is false. So alternative hypothesis is true. But the evidence from the sample did not lead us to reject the null hypothesis. So we failed to reject the null hypothesis, okay, when the null hypothesis is actually false. Okay, so that's called a type 2 error. Let me highlight it because it's very important. Again, today is a big day of lots of definitions. Okay, so in our case, with coming, the majority thinking that we're ready to come back, not, at least in months instead of weeks. So in that case, a type 2 error would mean that we weren't able to say the majority are think that we're going to be months and not weeks to come back, when in fact, the majority does think that it's not going to be months. Okay. So what's going to happen there is we're probably just not going to publish an article. So that's what it would mean. It just means that you wouldn't publish the article because you don't have evidence to say the majority. Doesn't mean that you have evidence to say that it's 50%. It means you don't have any evidence. So you probably won't publish the article, but your idea was actually right. And that sucks too, right? Because then you're right, except that you didn't have evidence to show you're right. So that means you weren't able to let everyone know about it. What about for the virus? What about for the testing at LTCC? What's kind of the analog of a type 2 error in this case? What do you call it? And yeah, that's called a false negative. Okay. What would the ramifications be of a false negative? Yeah, so that means that the person's going to get tested, and then I don't know how long it takes for them to do the test at LTCC, but let's say they get a call in the evening because they've finished the test, or maybe it's immediate. Anyone know? Is it immediate, or does it take time? I have no idea. So let's say it's immediate. It's easier to say. So you get tested, and you have to finish the test. I don't know about our test. I'm not sure. So you get tested, and then the nurse or doctor looks at you. Takes 2 or 3 days for results. Okay, calls you up in 3 days and says, you know what? You tested negative. So what are you going to do? Yeah, party. I like that. Okay, you get a party. You're going to be a lot less careful. And then what's going to happen? What are the ramifications? Other than you get to have fun partying. Yeah, it means all of your friends all of a sudden are going to get it and you're going to kill people. Okay. Okay, both type 1 and type 2 have ramifications. The ramifications are different. Okay. Yeah, I'm not going to get into the details of the medicine stuff. We're just doing statistics. Okay, so I'm keeping it simple. But that's kind of what's going on. Is the type 2 error in that case means that you're going to give them the ticket to go party, okay, or at least go to this grocery store, even if they're not going to party, and maybe do some other things too, because we're somewhat opening now. And then guess what? The person's got it, and all these people can get infected. Okay, it sucks. It's going to be very bad. Okay, first thing I want to look at our example. And actually, let me do one more type 1 and type 2 example. A real something that happened in the past. It's one of my favorite examples. And that happened in Africa. Okay, by the way, the coronavirus is what we're all worried about. If you lived in Africa for the last 30 years or so, what is the bigger worry that you might have, especially being single? Okay, being single, that's a hint. Yeah, HIV. HIV. Okay. Yeah, so they did it. So let me tell you what happened. So they did a test, and they thought that maybe having a circumcision will help prevent the spread of AIDS. Okay. Do y'all know what a circumcision is? So I don't have to get detailed. Okay, good. Maybe having a circumcision will stop the spread of AIDS. Okay, so what they did is they did a test, and they found a bunch of volunteers. And by the way, you can imagine being an adult male and volunteering to get circumcised. Okay. Okay, this happened. Okay, this is not like some fantasy. This happened. Okay, this was a while back. AIDS was much worse then. Just people were dying left and right. Okay, and as bad as circumcision sounds, AIDS was a lot worse. Okay, and what would a type 1 error be in this case? What would the ramifications of a type 1 error mean? So I like this example because it's very easy to remember the pain. Okay, what would a type 1 error be? Okay, any thoughts? Yeah, it means that a type 1 error means you don't reject circumcision. Actually, type 1 error means that you're going to think that circumcision works when it doesn't. And then what's going to happen to all these poor men? They're going to have to go through adult circumcision when it does nothing for them. Okay, is that a good thing, by the way? Okay, that's really horrible and painful. Do y'all agree? Okay, how about a type 2 error? What would a type 2 error do? What were the ramifications of a type 2 error? Yeah, that's the rejecting circumcision. That would be saying that circumcision isn't really changing anything, right? It's the same whether you're circumcised or not. And actually, it helps prevent AIDS. Okay. So, which is worse, by the way? Okay. So again, the ramifications of a type 1 error is you have a lot more people getting AIDS than need to get AIDS, or than would otherwise get AIDS. I think is a better word. Which is worse, type 1 or type 2? Yeah, type 2 error is worse in this case. Okay, so in that case, type 2 error is worse because if you get AIDS, you die. Okay, especially then. Now they have a cure. It's still awful, by the way. Okay, on the other hand, if you get circumcised, it hurts a hell of a lot. It's no fun, but at least you don't die. Okay, so that's definitely one where a type 2 error is much worse. So I want you to be able to look at the study and decide which is worse, the type 1 or type 2. That's what we're getting into next. So step 4 is to decide on the level of significance. And I do want to let you know, it is actually more complicated than what we're doing in our class. But what we're doing, we'll mostly do what you need to do. So the first thing is for our class, okay, and pretty standard, 0.05 is standard. Okay, looks two does. So it's a standard level of significance. Any questions on that? Okay, we talked about that before. Just like 95% confidence is the standard level of confidence. 0.05 is the standard level of significance. All right. So it turns out that a type 1 error, let's go back to the picture again. We have to decide what to make this rejection region. And the idea here is that if we take this line and move it closer to 0.5, that means we're making the level of significance as 0.05 bigger. Do you see that? Because there's more area outside. So that means you're going to have a bigger chance of rejecting. And if you have a bigger chance of rejecting, you'll have a bigger chance of a type 1 error. Any questions on that? Similar, if we take this line and we move it to the right, you can have a smaller level, a smaller chance of rejecting. You can have a smaller level of significance, and that means that the type 2 error is going to be a bigger error. So kind of putting that together, if the type 1 error is worse than the type 2 error, then choose. So that means we don't want a type 1 error. So we're going to choose 0.01 as the level of significance. Okay, if the type 1 error, actually let's go 2, error is worse than the type 1 error, what do you think you might pick for the level of significance? What number? So type 1 was worse, we went to a 1% instead of a 5%. If type 2 is worse, what do you think we're going to go to? Okay, that's a good guess. People tend to like to round a little more and go 10%. You could do 9%, but 10% is more standard. Use a 10% or a 0.10 level of significance. If they are similar, then use 0.05. Any questions on this? So how about our example when it comes to, deciding whether the majority think that it's going to be months, not weeks, to open up again? What do you think you'd use? 0.01, 0.05, or 0.10? Give it a guess. Hey, you got at least 1/3 chance of being right, even if you don't know. So what do you think you'd use? Yeah, 0.05 in this case. And the reason why I know it's 0.05, this is just to do a newspaper, just to do a news article. That's all they're doing, right? They're not making any decisions, just doing a news article. Okay, there's not a whole lot of damage done in either direction. Do you agree? And if there's not a lot of damage done in either direction, then 5% level of significance, you just do that. And that's standard. News articles always use 5% level of significance. That's standard. Yeah, so a type 1 error would mean you'd end up publishing that the majority of people think that it's going to take months. When it doesn't, and if people found out, then you'd have to be embarrassed because you published something wrong. No one dies or gets hurt or anything. A type 2 error means that you don't really have enough evidence, your sample size is too small, and you don't publish the paper. And again, no big deal happens. Do you agree? This example isn't one that's going to kill anyone or anything in either direction. Okay, very different than the AIDS example that I talked about. In that case, a type 2 error is much worse. So you might want to go to 10%. You might even go a little higher than that. Okay. And in fact, what they really did is they stopped the study midway through because it was so promising, they just went for it. And it became, at the time, practice to get circumcised because it helped prevent it. So it was kind of neat. I read that in the news. So that was one of those where they actually stopped the test in the middle because it wasn't fair to have some people get circumcised and some people not get circumcised when they found out it actually helped. Okay, and AIDS was so bad, especially when they were doing it in Africa. Okay, it's nothing like America. Okay, yeah, yeah, it was true. It doesn't mean it stops AIDS completely, by the way. If you've been circumcised, that doesn't mean you should go out and like have adventurous sex with 75,000 people. Don't do that. You can get other things. Syphilis, by the way. Syphilis is really bad in Tahoe, by the way. Just let you know that. I have a nurse friend. She says right now, half her patients are coming in for syphilis. Just a warning. Be careful. But AIDS is nasty. Okay, so that's why they just did that, because they didn't want to wait 2 years. And why do you think the same thing might happen with the coronavirus vaccine? Any thoughts? Okay, it's another one where a type 2 error is really bad and a type 1 error is not as bad. Because a type 2 error means you have a vaccine and you don't give it to anyone because you don't know if it actually works. Okay, and if that happens, then this virus just keeps happening. Okay, whereas a type 1 error means you think the vaccine works and it doesn't. That's bad, but not as bad. Okay, it means people think that they won't get it, and then you're gonna have a bunch of people get it. Okay, but basically you're gonna have what it is now, maybe in one more outbreak. So it turns out that a type 2 error is worse, and that's why they're trying to make the test fast. Okay, so just a note that this is all happening. Any questions on number 4? Okay, number 5. So number 5 is do the sampling, collect the data. Okay, I want to mention something that's really important. When you're doing high confidence intervals, you decide on whether you do 90% or 95% or 99 after you collect your data. Okay, when you're doing hypothesis testing, you decide on whether you're doing what level of significance, 0.1, 0.05, or 0.01, before you collect the data. Okay, very, very important. Okay, so the order matters. You're going to have to do a project. And guess what? You're going to do confidence intervaling, confidence intervals, and hypothesis tests. And you're going to have to decide on your level of significance before you collect your data, and you decide on your level of confidence after you collect your data. Okay, and you should talk about doing that when you write up your project. So that's just a note. Collecting the data, the funny thing is there's not much I need to say about it, but of all these parts, collecting the data is the hardest. Collecting the data could take years sometimes, whereas it could take maybe 10 minutes to do all the rest, maybe an hour or 2. Okay, does that make sense? Getting a sample size of 2,000, that is hard. So just because I only wrote 3 words and not doing anything other than writing it, I want to let you know that's actually the hardest part of the whole thing, is number 5. Okay, it's just not theoretically hard, but it's physically hard, practically hard. Any questions on number 5? Okay, number 6. Number 6 is calculate the test statistic and the p-value. Okay, so let me go to the picture again. And now I'm going to edit it. We have more things. It's going to get a little busy. Sorry about that. But there's a lot of stuff going on. Okay, so this was before we even started, we can draw all this out. Okay, before we collect the data. Once you collect your data, then what you're going to do is you're going to get your value, your proportion, your sample proportion in this case. And let's suppose that was where you got your sample proportion. Okay, so the first thing is that the t-value is a lot like the z in normal distribution, except you're typically going to, actually for this case, it is going to be a z. It's going to be the z in, kind of made as a z-score. So given a mean and standard deviation, what is the z-score of that point? And we've talked about this before, is that if you're more than 2 standard deviations from the mean, then it's an outlier, right? That's kind of rare. There's your 5%, by the way, typically. That's a two-tailed test, by the way. Any questions on that? Okay. And your p-value is going to be the area. Let me scribble again. That area, whoa, didn't let me scribble. Looks like I have to multiple scribble to make it happen. Okay, that area is called your p-value. Okay, so the area is going to be the p-value. If you have a right-tailed test, it's the area to the right of that point. If you have a left-tailed test, it's the area to the left of the point. If you have a two-tailed test, what you do is you draw your point, and then you reflect a point across the mean, and then you go left of the reflection plus right of the reflection. Combine those two areas, and that's going to be your p-value. Is it t for proportion, z for proportion, t for mean? Yes. Yeah. And that, remember, that's because we're able to use the central limit theorem, and we're able to say that we know we're going to be able to know the normal distribution for proportion. But for mean, you don't know the standard deviation, and that's why we had to use t. So the math is real complicated, so I'm not going to get into the math. Just kind of know that's when you do it. So for proportion, it's going to be z. For a mean, it's going to be t. And by the way, we're going to have more stuff. We're going to have 2 more letters later in this class. Not today, but in a few more weeks. So that will be another day. So be ready for it. Okay, for different hypothesis tests. Any questions so far? Okay, so we're going to calculate the test statistic and the p-value. Now, you're going to do that using a hypothesis test calculator, for sure. Okay, maybe I'll do that now. So let's take a look at the article again. And what we can say is, you have to read a little bit more. I think it gives you the percent somewhere in here. Here we go, there's 2,800 registered voters that were asked, so it's a pretty good sample size. Okay. Any questions on that so far? Okay. And do they say, they do it by state. So maybe I'll pick a state. I'll let you pick. Do you want New York, New Jersey, or Connecticut? Those are the 3 states they looked at. Sorry, we can't tell because they didn't look at us. NJ, NY, or CT? And we'll do one. Okay, let's do New York. So New York got 58%. Okay, 58%. And I don't know if they have the sample size of each of those, so I'm just going to divide by 3-ish. Let's just say it was, I don't know, 930 is about a third of the 2,800. So the question is 58% more than 50%? You better all know that. Is 58% more than 50%? Yeah. Does that mean we get to reject the null hypothesis because, hey, it's majority, it's more? What do you think? Okay, what do you think? Is that all we need to do? Okay, no, it's not all we need to do because getting a majority for the sample is not enough. It has to be so much farther away from 50% that the probability of having a sample being that far away from 50%, if it were 50% for the population, is too small, in this case, under 5%. So again, we're going to use 930 and 58%. So let's go to our calculator. Okay. So what we're going to do is we're going to do a hypothesis test for a proportion. So n, we're going to say it was 930. X X should be 58% of 930. So we're going to actually have to do a little computation here. It's not hard. 0.58 times 930. And you get 539. I'm going to round. Because it has to be a whole number. Our P naught, that is 0.5. So that's in the H, that's the P for the H naught. Okay. Is it less than, greater than, or not equal to? Which do we choose? Yeah, this one's greater than because that was what our H naught, our H1 was. And there's our test statistic, and there's our p-value. So the test statistic is 4.85 about. Let's write that down. So Z is about equal to 4.85. And then is the p-value 6.08 about? Okay, definitely not. Okay, first thing, P is a probability. P stands for probability. Can't be 6.08. What are you missing? And this is really important. It happens a lot. Right there. Okay, don't forget to look for that E, because that changes everything. Okay, it's not even 0.006. We got to move it 7 places. The first place is free, and then you get a 0 each of the others. You have 6 zeros and then a 6. P is equal to 0.1, 2, 3, 4, 5, 6 zeros, and then a 6. Any questions on that? All right, so then what we're going to do is we're going to decide whether to reject the null hypothesis or whether we're going to fail to reject the null hypothesis. Any questions on the next step? And as I mentioned, it has to do with this picture. So in this case, if our test statistic is to the right, or in other words, if our p-value is really small, very small probability, smaller than 0.05 in our case, then we're going to reject the null hypothesis because it's rejection region. Okay. On the other hand, if it's bigger than 0.05, we're going to fail to reject. So we write that in general, and then we'll do it specifically. So if P is less than alpha, alpha is the level of significance, by the way, reject the null hypothesis. I'll just write null. If P is greater than alpha, fail to reject the null. Okay, so in our case, 0.60 and a 6 is much less than 0.05. Do y'all agree? Okay, so we reject the null hypothesis. Any questions on that? Okay. Step 8. Step 8 is state your conclusion. I just got a note. My screen is blinking a lot. Is it blinking for all of you too? So is it my internet or hers? There's nothing I can do about it anyway, but okay, it's not blinking. Sana, you have a slow internet. That's what that means. A slow internet. Even if it was blinking because of me, I can't do anything. It's internet. I'm at home. But fortunately, it's just it's your side on it. So state your conclusion in the context of the study. So in this case, what we say is there is, and I'm going to use the word strong. Strong because it's not just less than 0.05. It is really small, okay? Typically, if it's smaller than 0.01, we can use strong. Statistically significant evidence to conclude that the majority of all Americans, actually of all New Yorkers, because this is what we looked at, of all New Yorkers think that it will be months, not weeks, until we reopen. Okay, so I want to note that when you state your conclusion, if you're less than 0.05, in this case, that means we say we have statistically significant evidence. And then you conclude, and what you do is you just write down your hypothesis in words. Okay. If instead our p-value was large, let's say our p-value is 0.25 or something, which would be bigger than 0.05, then the conclusion, actually, next line, then the conclusion would be there is statistically insignificant evidence. And you would say to make a conclusion that the majority of New Yorkers think that it will be months, not weeks. So that you put the two little words in there I'm not going to because that's not what we got. But if you get a large p-value, then it's insignificant instead of significant. Any questions on this idea? Any questions? Okay, so that's the main thing, but there's a couple more items. This is sometimes I'll ask you to do, sometimes I won't. And that is interpret the p-value. So again, let's go over to the picture. Our p-value is this probability of being over to the right of this dot, given 0.5 was true, right? We use that 0.5 was true to even draw the picture. And that's kind of how it's going to work. Now, sometimes it'll be to the left, sometimes it'll be farther than a certain amount on either side. In this case, it's to the right. So it's got it kind of similar to the confidence level. So in this case, what we can say is that if 50% of all New Yorkers, because that's what H0 is, think it'll be months, not weeks, to return or reopen. And if we did or conducted another study or survey, I guess in this case, of, I think we said 930 New Yorkers, then there would be a And the p-value is like really small. So that's almost 0%. So in this case would be nearly 0%. Okay, if it was say 2%, then you go 2%. In this case, it's nearly 0% because it's so close. Chance of having at least 58% of this new sample think that it'll be months, not weeks, to reopen. And any questions at all on interpreting the p-value? Okay, let me do another one. Number 10. Today's a long day, by the way. A lot of things. One example, lots of things. Okay, and next time I'll do the same thing with lots of examples. But the idea is hopefully at that point you'll at least have seen an example in full. Okay, so interpret the level of significance. Okay, so the first thing is the level of significance is the probability of a type 1 error. So now we just remember what that means is that the first thing is what we can do is we can start the exact same way that we did with interpreting the p-value. That is, if 50% of all New Yorkers think that it would be months, not weeks, to reopen, and if we conducted another survey of 930 New Yorkers, then there would be, okay, now the level of significance here was 5%. A 5% chance that the new study would lead us to falsely conclude that more than 50%, or the majority of New Yorkers think it will be months, not weeks. Any questions on this? Let me do one more. I know you're getting tired probably because there's so much stuff here. Okay, the next piece is, was the sample size large enough? This is often done at the very beginning, by the way. So was the sample size large enough? And the idea here is you already know how to do this. How do you tell if the sample size is large enough? You remember? Yeah, NP and NQ. I think you knew what you're talking about, but you typed it wrong. NP and NQ are greater than 5. So NP, in this case, was equal to, we actually already did that. That was 539, because that was our X. And NQ is going to be 930 minus 539, which is 391, I think, are both larger than 5. So the sample size was large enough. Any questions on number 11? Okay, let's do some more. Again, I'm going through one example in full, all the different things I could ever ask you, basically. Okay, number 12 is which error is still relevant? Type 1 or type 2? Okay, and the idea is before you collect your data, they're both relevant. After you do your analysis, only one is relevant. Which is relevant now? What do you think? You got a 50-50 if you guess. Which one's relevant? Yeah, type 1 is relevant. Okay, so in this case, only the type 1 error is relevant since we rejected. It's kind of like if you went to LCCC and you got the coronavirus test, and then the doctor, calls you in 2 to 3 days and says, we have great news for you. Tested negative. Do you worry about a false positive? What do you think? No. If it tested negative, you didn't get a false positive. Do you worry about a false negative? Yeah, you have concern about a false negative, but once the test is over, the false positive is not relevant anymore because you tested negative. Do you see? It does not mean you have a false negative. It means there's concern that it's a possibility, a low possibility, but there's a low possibility. Here, what do you think? Is it a very high possibility? Is it a very, very, very low possibility? Or just a little bit low possibility? In our case, with this example that we just did with the New Yorker study. What do you think? Yeah, this one's very low because look at our p-value. Our p-value was minuscule. It's kind of like if I flipped a coin 20,000 times and got 19,999 heads, of course you think I'm cheating. And you're sure of it. Do y'all agree? There's a chance I got lucky, but not really. I mean, it was so low a chance that give me a break. Does that make sense? Okay, on the other hand, if you got 0.04, then you have a low possibility, but not a very low possibility. Any questions on this? All right, so just a note, this is important too. At this point, again, there's a concern of a type 1 negative error. But very low concern, since the p-value is so low. Any questions on that? All right, so I want to give you kind of a idea example of this kind of stuff. After doing this test, okay, after doing this survey, let's suppose you're the one that published this. You work for Quinn about, you're in charge of this poll. Do you feel that you need to redo the survey just to make sure? Or do you feel like you feel comfortable with the survey? What do you think? Are you happy with the survey, or do you feel like you need to redo it? Yeah, you should be happy with the survey, okay? In this case, you're happy with the survey, you rejected the null hypothesis, which is always your goal. So you're done, you're happy. What if you had gotten 0.04? Then do you think you need to redo the survey if your p-value is 0.04? Okay, yeah, still not. Because again, 0.04, you rejected the null hypothesis. Any questions on that? And you get to be happy. What if you got 0.06? Do you redo the survey? So redo the survey or not if you got 0.06? Yeah, at that point you want to redo the survey because you were close, but you didn't quite make it. You see that? You don't have evidence to publish your paper, and you're not going to be able to publish it. And you're like, man, but I still think it's true. What if you got 0.92? Do you redo the survey? Yeah, in that case, there's a really small chance you're right, but it's so minuscule, it's not worth your time. Okay, just a big note, if you got 0.06, should you ask another 930 people? That's the right thing to do. What's your thoughts on that? So if you got 0.06, should you ask another 930? No, it doesn't depend on the survey, actually, but it was a good try. Okay, the answer is no. Okay, the answer is you need to ask a lot more people. So you need to ask, instead of 900, more like 9,000. And here's the problem. If you're wrong, and let's say it really was 50%, and you keep asking 930 people over and over and over again, let's say you did it 100 times, then eventually you're going to get a type 1 error. And when you get that type 1 error, you're going to say, I was right, except you have a type 1 error. So each time you're going to have a 5% chance of having that type 1 error. And if you do it many times, then that chance of having a type 1 error gets bigger and bigger and bigger, and pretty soon it's ridiculous. So instead, what you do is you need to use the law of large numbers and get a gigantic sample size. So if you get 0.06, you cry because you feel like you're still right, and you have to decide, do I want to really push it and do 9,000 people, which is going to take huge amounts of effort, or do I just give up? Does that make sense? Because going to 9,000, what that does is it takes your standard error and makes it smaller. Remember that sigma sub x bar, sigma over root n kind of thing, or it has to do with the dividing by root n. So if you are needing to redo the survey, you need to get the standard error smaller. And the only way to do that is with a bigger sample size. So the standard error has everything to do with the hypothesis test. And by the way, it does with the confidence interval too. Large standard error makes your confidence interval higher, or wider is what I meant. Any questions at all on that idea? It's one that people have trouble on the project with. because I'm going to require you to write about it. Any questions? Okay, so this is pretty much everything you need to know about a hypothesis test. I did one example today because I really want to do it in full. Next time, we'll just quickly go through a bunch of examples, but not do all the long explanation of what stuff is. And I'm going to have you do some work next time instead of me just let you know that. The other thing is this is for a proportion. Do you think things change that much for a mean? What do you think? So if it's quantitative in terms of these steps 1 through 12 or whatever, do you think there's a whole lot that changes? Yeah, not that much. The main thing that changes is the symbols. You don't use P, you use mu. Okay, but otherwise everything is basically the same. There's not much of a difference between a mean and a proportion. I will let you know, just so you can get ready for it. What do you think the quiz is going to be like? On Thursday, by the way. Any thoughts? I'm going to give you a question that's hypothesis, and you have to do all the steps. It'll be a proportion because that's what we did. Okay, you can expect the next quiz after that to be mean, but this one will be a proportion. Okay. There's a lot. Yeah, I mean, remember, I spent a lot of time talking about all this stuff, but some of these are real quick. Okay, collect the data you won't have to do. I'll give you the data. I'll give you what the sample was. Okay, so I'll have you answer some questions. I don't know about all of them, but a lot of them. But the ones for sure are find the Z and the P. That you have to do on every hypothesis test, basically. You're definitely going to have to state your conclusion. That's the punchline. If you don't know a punchline, then you don't have to tell the joke, right? So you definitely have to know how to state the conclusion. Those are the main ones. 9 and 10 are maybe. I don't know about 11. We've already done enough. I may not need to ask it. And 12 is a maybe. Sometimes I do 12 and then I don't do 3 because 12 revisits 3. Okay. Any questions? Any questions? We've kind of done all the minutes we're supposed to do because we didn't take a break, which means that I should leave a little earlier, but I also have office hours. I'm going to leave my screen share. And undo the pause recording.